Okay, class. Let's see, we're pushing on a little bit here, trying to get to the end of the antennas material, at which point we'll need to have some sort of an exam yet to be determined exactly how we'll do that, but nevertheless, we'll proceed. Right? So the next topic of discussion is antenna arrays, right? So we talked about antennas, but you can put antennas in arrays and therefore increase the electrical aperture size and therefore increase the directivity, right? Because we saw that the directivity was 4 pi times the effective aperture over the square of the wavelength, right? So area divided by wavelength squared is electrical area, or the number of the size of the aperture in square wavelengths, and so the directivity is directly proportional to that, right? So when you add elements in an array, then you're essentially increasing the electrical area and thus increasing the directivity, right? Or equivalently decreasing the half power beam width of beam radiated by the array. Okay, so that's one fundamental reason why to have arrays. The other, of course, is the fact that by adjusting the relative phase shift of the elements in the array, you can actually steer the main beam in space without having to mechanically uh, adjust the array, right? You don't have to turn the array in order to get the beam. You don't have to physically turn the array in order to get the main beam to point in a different direction. Now, sometimes, you may spin the antenna array in azimuth, right? And then you may control the direction of the beam and elevation using phasing. So there may be some combination of physically turning the array and electrically scanning the beam. Right? So all sorts of variations on the theme there. But right, the two major reasons why we have arrays are A, increased directivity, B, the ability to scan the beam in a desired direction using a linear phase shift down the elements of the array. Okay, so that said, there's another principle, right, that we call pattern multiplication, right? And pattern multiplication basically says that, hey, if I have an array of elements, right, like that are shown here, then if I want to compute the pattern of the array of elements, then I can take the pattern of one of the elements, in this case, something like a half wave dipole, say, or an infinitesimal dipole. The patterns of a half wave dipole and an infinitesimal dipole are not significantly different. Recall that for the half wave dipole, it's got a little more directivity than for the infinitesimal dipole or ideal dipole. So anyway, back to the discussion at hand. The pattern from the array of elements is the pattern of one of the elements times, right? So we're going to multiply patterns here. So this is why we call it pattern multiplication, right? Of isotropic point sources that are placed at the phase centers of these antennas, right? This one goes with that. This one goes with that antenna. This point source goes with that antenna. And then these isotropic point sources have the same phase relationship as the currents fed into the actual antennas have. Okay. So, right. So, for example, in this case, this antenna has driven at some current amplitude of 1 at an angle of 0. This current is, say, 1 at an angle of alpha, and then this current is 1 at an angle of 2 alpha. So you see that the phase increases or perhaps decreases if alpha is negative linearly along the line of the array. Okay, so the line of the array is ordinarily the z-axis, right? And then we measure the pattern up as a function of theta up from the z-axis. Right. So this concept of pattern multiplication, and if we're interested in studying the pattern of an array of antennas, then part of that is going to be understanding what the pattern of an array of isotropic point sources looks like. Right. Now we're going to restrict this somewhat. Right. We're going to allow we're only going to allow the spacing between elements to be uniform, right? In other words, they're going to be equally spaced, and we can relax that later on, and I can show you ways to do that. But for now, let's take the simple case, and the simple case basically contains everything that we need to know anyway, at least at this level. We could dig into it in a deeper way later on. But in any event, right, the spacing between elements is going to be uniform, right? The amplitude of the elements are going to be the same, right? So we say UE, uniform excitation, and then we say ESLA, equally spaced linear array. So uniform excitation, they all have weight 1, uh, equally spaced, they're all equally spaced between the elements of the array of point sources, and it's a linear array, they're in a line. In other words, we're not allowing them to fall outside of the z-axis. And that can be relaxed pretty easily as well. You study planar arrays or volumetric arrays. The concepts in order to extend this are pretty straightforward, but you learn quite a bit just from this case. Right? We'll get a pretty good feel for how to change the main beam direction by adjusting alpha, right? And we'll be able to determine the shape of the pattern using a graphical technique, which is pretty useful by simply knowing the number of elements. In this case, we show 3, the spacing between elements, and the linear phase shift of the elements down the array, assuming again that they're all uniform, that it's uniform excitation. Okay, so what we're about now is to determine the pattern associated with an array of isotropic point sources, right? So each one of these, if you looked at the pattern of each isotropic point source, it would be just a circle, right? Because it is isotropic. That means it radiates equally well in every direction. But because of the spacing between these, and because there's more than one, and because of the phase shifts, in some direction, right? In some directions, the fields from these point sources are going to add constructively. In some directions, they'll add destructively. So there'll be points in space where you get a maximum, and there'll be points in space where you get a minimum, and then there'll be points in space where you get something in between the max and the min. Okay, so right, here we go. Here's our array of point sources. That's what we're studying. Right, we'll do the product later on, but for now we're just looking at the array of isotropic point sources. Right, spaced by d dot dot dot. So there's going to be n of these. Right, this element is the reference element, so it's 1 at an angle of 0. Remember, they're UE, uniform excitation, so they all have weight 1. Right, and so the second element along the z-axis has weight 1, just like the primary element or the reference element, but it has a phase shift, a possible phase shift of alpha. So it may lead or lag. If alpha is negative, it'll lag. If alpha is positive, it'll lead the source phase here by alpha degrees or alpha radians, depending on how we express it, right? And then this one leads that one by alpha, or it leads the reference element by 2 alpha. And so this is a linear increase in phase as you move down the array, right? So here are the rays, right? These are called rays. Here are the rays from these point sources out the direction theta,